I read the brief for this very quickly, so I might have done the wrong thing. Sorry if I have. I'm going to tell you about my thesis. So I've been looking at memory consistency models. And for those who don't know what memory consistency model is, it's a set of rules to tell you what a load will give you when you ask memory what's stored at some given location. And it's interesting in concurrent systems because you might have multiple actors modifying the same location at the same time, and you want some rules for delegating whether that's legal and what you might see there. And these rules end up looking like a big pile of mathematics. There's some relational algebra and rules about the structure of those relations called axioms. And that's the traditional way that hardware is specified and programming languages have been specified. And there's lots of tooling to take in these specifications and a huge amount of academic research from many people in this room and people outside this room as well. And this tooling's been really successful. These mathematical models are hard to evaluate for experts, and they are borderline impossible to evaluate for programmers. And tooling helps a programmer write some code and answer a question. There have been some new models recently trying to solve the out of thin air problem, for which there's been very little tooling built. I skipped a slide. Maybe I'll get there in a minute. But in my thesis, I went through 3 case studies. One was on the VeTSS memory model. So this is a hardware-ish memory model for the NVIDIA architecture. And I did an internship at NVIDIA, and they pointed out that there's some features in the hardware, particularly around graphics, that are just not exposed in the programming model. Graphics has a bunch of weird widgets that behave just a bit differently to normal loads and stores in a compute model that were hard to accommodate. They had irregular paths to memory that were non-coherent with regular loads and stores in compute. So we added proxies to the VeTSS model, which accommodates those and lets you, it builds an abstraction over the various different types of accelerators for graphics and now for machine learning that are integral in the NVIDIA architecture, but doesn't special case them individually in the VeTSS programming language. Right. Yeah, so after looking at a hardware model, I looked at some thin air problem things. So in programming languages, it's a bit different to in hardware models because there's a compiler that's changing your code. And at the top of this slide, there's a bunch of programs that are subtly different. The first program has unconditional stores to x and y. The second program in the center has conditional stores to x and y, where I've put the pictures the wrong way around. In this branch, they are, a compiler could optimize this out. And in the third program, the compiler couldn't optimize. And the thin air problem really is that from the perspective of a traditional axiomatic memory model, the memory model executions all look identical. One of these you want to disallow, and 2 of these you want to permit for efficient compilation to modern hardware. But if the pictures are the same, you can't write a rule to distinguish them. And this is intrinsic in the way that the axiomatic memory models work. Because they only look at one execution at a time, it's very hard to draw these pictures without forbidding optimizations that compilers do in practice. And we don't want to go and tell an army of compiler writers that they're wrong. They've been doing it for 50 years and are cantankerous. So an early proposal to solve the out of thin air problem for Java was Geoffrey and Riley's event structure model. They built a game semantics over an event structure, and this has a very different style to an axiomatic model. In axiomatic models, you quantify existentially over a bunch of relations and then apply axioms to those relations. Whereas in Geoffrey and Riley's model, because it's a game semantics, there's this taking turns between the player and an opponent. And in mathematics, this is alternation of quantification, exists for all exists. And that changes the class of problem a bit. So in axiomatic models, you can run them through SAT solvers or over fairly naive algorithms and get really quite good performance. But if you can't do the same thing, you can't run the Jeffrey and Riley model in herd, you can't encode it in relational algebra. And if you try and feed it to a SAT solver, you've got to expand one of these levels of quantification, which means that your SAT query is far too large. So we found that working through this in second order logic worked better, and we could use new second order logic and QBF solvers to evaluate the Jeffrey and Riley model automatically over a corpus of litmus tests. And as far as I know, this is the first thin air free memory model that had tooling to automatically evaluate it. There's a tiny bar chart in the corner that shows that it's slow. It's much slower than herd because it's doing a class of problem that is more difficult than herd. Herd is fantastic at evaluating axiomatic models quickly over litmus tests, but it can't handle these alternating quantification style models like Jeffrey and Riley's. And then as a final case study, as collaborators in the room, we looked at modular relaxed dependencies. So this was a C++ model, or rather it was a model for a language like C++, and we could extend it with the C++ axioms to make it a full C++ model. So C++ has this thin air problem, and one of the proposed solutions is to say that program order and RF be acyclic. So on this slide, it would ban all three executions, including the two that are desirable as a result of compiler optimization and of hardware implementation. We didn't want to use PORF acyclic, so we need to think of something else. And one of the choices you can do is to say that dependencies union RF are acyclic. The problem is knowing which dependencies preserved by a compiler is very, very hard, because compilers can do essentially any chain of reasoning possible to remove a dependency and generate faster code. So modular relaxed dependencies is an attempt to build that. And alongside it, there is tooling to automatically evaluate it over a corpus of litmus tests. And that tooling was really useful. Building tooling alongside the mathematics meant that we could catch bugs early. So where the mathematics was doing the wrong thing on litmus tests, we would find out before we try and do huge formalization effort or get a bunch of bad reviews back. And it has helped us communicate a very, very complicated idea to people outside of the direct niche within a niche in this room. There are folks at ISO who want to understand what's broken about C++ and why the thin air problem is a problem for them and how it might be solved. And being able to say, well, this line change here, along with a definition for semantic dependency, can work, and here is a definition of semantic dependency that is admittedly impossible to understand, but there is a tool to automatically evaluate it, so you can put in programs and play with it, has been extremely valuable. So in the spirit of this being vets and everyone giving you opinions about what's good about research, I'd say that in my thesis I found that tooling was extremely helpful in not only developing formal models and checking that they are up to muster, but also communicating them and getting impact out of academic research. It's very nice talking to everyone in this room, but it's much more useful if you can affect change outside the room as well. And VETS also drives impact. VETS is a platform of providing small grants to early career researchers, particularly with an impact focus, without huge bureaucracy, has been extremely valuable. VETS has supported my research as I've grown in my career, and I'm extremely grateful for that. But in particular, it's also instilled within me some understanding of how research can make the world a bit better. And I don't think that would be possible without VETS. With that, thank you very much. I'd like to thank my collaborators, including Alan Jeffrey, who is no longer with us, I'd like to give special thanks to VeTSS, to my friends and family, and of course Mark, who was an excellent PhD supervisor. Thank you all very much.